Welcome to the next lecture in our Essential Statistics course, Analyzing Dichotomous Data. We are slowly filling our table of different testing scenarios here. In the last lectures, we already covered, as a first example, tests when the dependent variable or the outcome variable was continuous, and our predictors or independent variable was discrete. So, for example, the two-sample t-test, the paired sample t-test, or their non-parametric alternative, the Wilcoxon-Rank-Sum test. And finally, when you had more than two groups, an ANOVA test. We also covered the case of a continuous independent or predictor variable, namely looking at correlation coefficients and testing for their significance, and also looking at linear regression. Today, and in the next lecture, we will cover dichotomous outcome variables and look at the chi-square test today. This is a test where you can test the probability that of an outcome for a dichotomous variable if you have two or more discrete groups. Where do such dichotomous data occur, or what do we mean by that? We typically mean data that can take either of two values, for example, 0 or 1. One scenario where something like this could occur in your research is when you look at cells, like here, and you want to look at the fraction of cells that is positive or that shows a certain staining, like here, and compare the fraction of cells that shows that staining in two conditions. Let's say a control condition and a treatment condition. Let's look at the following example. Sometimes in soft drink dispensers, you may find bacteria. If you want to estimate the proportion with which that occurs in a study, some researchers sampled randomly 30 of these dispensers, and they found 5 to be contaminated. An obvious estimate of the probability with which this contamination occurs is the following. So our p hat is, like one would compute it intuitively, 5 over 30, or 16.7%. One can come up, however, with alternative estimates. And one alternative estimate for the fraction from a sample is here our p tilde, where we add 2 to the numerator and 4 to the denominator, resulting in dividing 7 by 34, or an estimate of 0.206 or 20.6%. It's important to realize that both of these are valid estimates. This corresponds to the case where to your sample that you observed, you add 2 positive and 2 negative fake observations. It will become more clear why we do that later. It biases our estimates away from 0 or 1 towards 0.5. So if we do this, we express our belief that the probability is somewhere around or closer to 0.5 than to the extremes of 0 or 1. We can take, as we have done many times now, take the point of view of a meta-study. We can ask, if we are in our statistical setting that we have a population that is an abstract quantity and we observe a limited sample and we want to go back, we need to look at the sampling distribution of this probability that occurs when we repeat the same study many, many times. One can show that the sampling distribution in the case of dichotomous data is in fact a binomial distribution. If we, say, have a sample with 20 dispensers, or if we have samples with 20 dispensers and a probability of 17%, then our sampling distribution might look like this. Again, as we change the number of samples in each of the samples in our meta-study from 20 over 40 to 80, we can observe that the width of this distribution becomes narrower and narrower. This is just analogous to the case of continuous data, where the distribution of the sample mean becomes narrower and narrower the more the sample size grows that we use to estimate it. Remember, and if you don't remember, go back and watch the video of the respective lecture, that the width of this distribution is our standard error of the mean. So we can compute also a standard error of the proportion. To remind you, we are in the setting where we have the abstract population. We observe a sample of size n, and we compute p tilde as an estimate of the true p in the population. To get a standard error of p, we compute the following. So here, on top, p tilde times 1 minus p tilde. You may remember that this is nothing else than the variance of the respective binomial distribution. And as you saw on the last slide, the sampling distribution of the population of the sample proportion is a binomial distribution. And then we divide by n plus 4, because we added in our estimate our 4 fake samples, and take the square root. So as an example, we have here 999 young mothers were asked about their smoking habits during the last 3 months of pregnancies, and 125 admitted smoking. So we would like to know what is the average probability, or what is the probability of smoking in that particular sample, and where do we expect the true population proportion to lie given that estimate. So what we compute is our p tilde, 125, we add 2 to get our regularized estimate, and 999 plus 4, so we divide 127 by 1003 and get an estimate of a population proportion of 12.7%, or 0.127. Now the standard error, we simply plug this value into our formula above. So 0.127 times 1 minus 0.127 is 0.11, and we divide by 1003. So our standard error of this estimate of the population proportion is 0.011. As we have done before, we can use this standard error to construct a 95% confidence interval for the population proportion. So, as before, we know that our p tilde plus minus 1.96 times the standard error, that this yields a valid confidence interval for p. So let's compute that for an example. So this gene BRCA1 is linked to breast cancer. And 169 women with a family history of breast cancer are screened for that gene, and 27 have the mutation. So we do our calculation as before and find that p tilde is 29 over 173, or 0.168%. We then compute the standard error of the proportion as 0.168 times 1 minus 0.168 and divide by 173 and take the square root. So that is 0.028. Now we can specify our 95% confidence interval, and this works as follows. So we simply say our 95% confidence interval is 0.168 plus minus 1.96 times 0.028. So that means that we are 95% confident that our population proportion is between 0.113 and 0.223. And we can summarize this in a summary sentence saying we are 95% confident that the probability of having a mutated BRCA1 gene in women with a family history of breast cancer is between 0.113 and 0.223. If you're not sure anymore about the interpretation of confidence intervals, remember the analogy of the dog with the invisible man. The idea was that a dog that you can observe, this is the sample, is attached to a dog owner with an invisible leash, and the dog owner is also invisible. This is the true population proportion, with a leash that is spring-loaded, so that always pulls the dog back to the dog owner in a way such that in 95% of the time it is within 2 plus minus 1.96 times the standard error. So now let's come back to the question we had in the very beginning, where we introduced this adjusted estimate. Why did we do that? Why do we use an adjusted estimate at all? So as many people will know now, an ECMO is a machine that can be used to, in case of severe respiratory failure, also in babies. And in this study, 11 babies were treated and none of them died. So if you were to compute the naive estimate of the sample proportion, you would say, well, 0 over 11, that's 0. If you do that, your 95% confidence interval is also 0. And that would imply that from that limited sample of just 11 babies, you conclude that in all eternity, you will never observe, you're very confident that you will never observe any babies dying when they're treated with ECMO. And of course, that doesn't even make sense intuitively. And there are also good mathematical reasons not to use this estimate, therefore. So when we use our adjusted estimate, because it's a regularized estimate or a biased estimate towards 0.5, this allows us to say, well, we just observed 11 babies. This is limited evidence. We add our 2 fake samples to both the positive and the negative outcomes, and then this yields our adjusted estimate, given our limited data, of 0.133%. What you will also notice is that as your sample size grows towards infinity, the contribution of these biases that you introduce into your estimate, they become vanishingly small. If you divide 10,000 over 100,000 and add 2 to both, that almost doesn't matter. So instead of an estimate of 0 with a confidence interval of exactly 0, in this case, we can also compute a standard error of the mean, which is 0.088, and a confidence interval 0.133 plus minus 0.172. And because this goes negative, we just simply clip it at 0, and we can specify we are 95% confident that the probability of babies dying at an ECMO is between 0 and 30%. And this is a statement that makes much more sense than saying, just by observing 10 babies, I will conclude that babies are safe when they're treated with ECMO. Because, in fact, they are really severely sick when they're treated with ECMO. Good. So now we are able to estimate or provide a regularized estimate of a population proportion and an associated 95% confidence interval. Another question that in such cases we often have is, how can we test whether P differs between 2 groups? This was also the case in the motivating example that I showed you on the first slide. For example, when you count how many cells died under a certain treatment and how many survived. Here is an example from the book about a reduction in migraine headaches. A team of doctors suggested a surgery to reduce the severity of the headache. And in a study, they did a total of 49 real surgeries and 26 sham surgeries. The question was, in the end, was there a substantial reduction in migraine headaches? So the sham surgery group takes the role of a control group here. Now, if we simply compute the probabilities, we find the probability of success given our real surgery is 41 over 49. So here we use the naive estimate, or 83%, while the probability of success given the sham surgery was 15 over 26, or 57.7. We can plot these two quantities here in a sort of a bar graph. Now, we cannot simply use a t-test to compare these, because, as you might remember, the prerequisite for using a t-test is that the data is Gaussian distributed. Because these data are binary, it's either a success or not, the dependent variable, we cannot simply use a t-test. So what do we do instead? How do we say whether this difference here that we have observed in our sample, that is in fact statistically significant or not? The test that we use for that is the so-called chi-square test for the 2x2 contingency table. And I will take you through the steps of that test now. So this is how a 2x2 contingency table looks on an abstract level. And we will make a concrete example in a minute. Here in this row, we have our experimental group. It's either C or not C. Here we have the observed outcomes. And it's either some event happening or the event not happening. And in these cells, we have all the respective conditional frequencies. So here, for example, we have the number of times that the event E occurred, given that an individual was in experimental group C. Here we have the probability of the event E occurring, given that the individual was not in group C. If we sum across these rows, we get the column total of how many individuals were in experimental group C. And if we sum across these rows, we get the column total of how many individuals were in group not C. We can do the same for the rows. So sum across these rows and get the row total. And here again, illustrated the column totals. And if we sum all the values together, these values or these values, we get the entire total. Now we want a test that allows us to answer the question, is the probability of the event occurring given that an individual is in group C, is that equal to the probability of an event occurring given that the individual is not in group C? The test statistic that we will use to test this is the following. It's called chi-square statistic, and it's the sum over all these entries here, over all these 4 cells. So this is indexed by the I. The I can take any of these values. And it's always the difference between the actually observed frequency or observed count with which that you find in this cell, minus the expected count that you would assume given the row and column totals. Divided, and that's squared, divided by the expected count. It's important that these are not frequencies, but they are actual counts. So this is the expected count under the null hypothesis, so under the probability, under the assumption that these two probabilities are the same. And this is the observed count that you find in the data. So how do you compute these expected counts, assuming the null hypothesis is true? Well, let's look at the expected count for this cell here, that the event or the sample has has the observed outcome E and is in experimental group C. So this is simply the total, the row total here times the row total there, divided by the overall count. This is what this formula says. So you just take the row total for E, you multiply by the column total of C, so the number of people in that group, and you divide by the total number of samples. Let's look at an example to make this more concrete. So again, we would like to know whether our real surgery is more effective than the sham surgery. Here I've already provided the solutions for the expected counts, but let's look at how we actually computed them. So the expected number of successes in the real group, so this is this cell here. This is the row total, so 56, times the column total, times 59, divided by the overall total, divided by 75. And this is 36.59. In addition, the expected number of successes in the sham group, so this is this one, is again the row total of success times, in this case, the column total of the sham surgery divided by 75, which is 19.41, and so on. And when you compute these values, you will get 12.41 and 6.59. Then, to compute our test statistic, we simply take these counts, and as I said on the last slide already, it's important that these really are counts. They are not frequencies. We take the difference between the real and the expected count if the null hypothesis was true, square it, divide by the expected count, and then sum these values up. And in this case, this would result in a test statistic of 6.06. Just to remind you briefly, what does the test statistic measure? The test statistic measures to what extent the data adhere to the null distribution, or to what extent the data is compatible with the null distribution. The chi-square test does that by explicitly computing the predictions for all the cells, if the assuming that the null hypothesis was true, and computing the deviations and simply squaring them. So what do we do with a test statistic once we have observed it? For a good test statistic, we are able to compute the null distribution analytically. So the null distribution was the distribution of the test statistic, assuming that the null hypothesis was actually true. And in the case of the chi-square test, this distribution is the so-called chi-square distribution with 1 degree of freedom. And as you have learned by now, you can use also JASP to plot that curve. And it looks like that. Because of the squares involved in the chi-square statistic, the values that the test statistic can take, or that the distribution can take, are only positive. In our case, for example, we could observe a chi-square value of 1, and then we would compute the p-value as the area under this curve here, this blue area, and that would be really large, would be 0.32%. 0.32. And this p-value would tell us that, assuming the null hypothesis is true, 32% of the hypothetical samples result in a chi-square test statistic that would be more extreme than the one observed in the data if chi-square was 1. But on the last slide, we computed our chi-square to be actually much larger than 1. We computed it to be 6.06. That means that the p-value is just this tiny area here at the very tail of the distribution, so about 0.01, which means that our p-value in this case is 0.01, and thus smaller than, let's say, an alpha cutoff of 0.05, which allows us to reject the null hypothesis. So we can provide a summary statement saying, the surgical procedure improved the migraine significantly compared to a sham surgery. P equals 0.01, N equals 75, chi-square test, probability of 0.83 versus probability of 0.58. Here I've summarized the two sample sizes into one number, but of course it's also possible and maybe desirable to report both numbers individually. So you can see the chi-square test also follows pretty much the same logic as all the tests that we've covered so far. For the chi-square test, you can think of two potential scenarios or two potential contexts in which such a table becomes relevant. The one that we have discussed just now is that of two independent samples that each have a dichotomized observed variable. So for example, for two treatment groups with cells, you could look at how many cells died and show a cell death expression marker. Or for the case of these surgeries for the migraine, you could look at what is, in each of these two cases, with a real surgery or sham surgery, what is the probability that, that either of them helped and was successful. But you can also have a case where you have one sample with two dichotomous observed variables. You can still use the chi-square test in that case to test for an association between the two variables. And the interpretation is more like that of a correlation coefficient. So let's say in this example here, we have two observables of people, of men, I think, in this case, hair color and eye color. This data was recorded somewhere in Europe. And the hair color is either dark or light, and eye color is also just classified as dark or light. So in this case, among our 6,800 individuals, we have two observables, and we want to know whether they are associated or not. It's not like the mechanics of doing that are actually fairly similar than to testing a difference between these two groups or testing a difference between these two groups. But the context is much more symmetric because these two are interchangeable. If one of them is an experimental manipulation, they are not easily interchangeable. So we can use the chi-square test as a test for statistical independence. So we can say, for example, or we can want to ask, for example, the probability of dark eyes given dark hair is 0.19, and the probability of dark eyes given light hair is 0.04. Is this difference statistically significant? Or equivalently, we could say the probability of dark hair given dark eyes is 0.85, and the probability of light hair given light eyes is 0.53. Ja, hier kurz. Nee, nicht zu Ende machen. Wir machen einfach weiter. Ja, genau. So the probability of dark hairs given dark eyes is 0.85, and the probability of dark hair given light eyes is 0.53. Now, our null hypothesis can be phrased in multiple different ways. We could either say our null hypothesis is eye color is independent of hair color. We can say hair color is independent of eye color. We can say, or we can simply say hair color and eye color are independent. Because in this setting and in this context, the two are symmetric. One has to be careful, though, to pick the right verbal descriptions of these associations. One way to phrase, for example, a possible outcome, in this case about color blindness, is to say color blindness is more common among males than among females. That's a true statement. You could also say maleness as a property is more common among colorblind people than femaleness. That's also true. You could finally say most colorblind people are male, but what is not legitimate to say, and does not follow from the above, is that most males are in fact colorblind. Because this is another statement than any of these. So one has to be careful of how one describes such associations. So let's look at the example of the dark eyes and the dark hairs again. So in this case, the probability of dark eyes given dark hairs is about 19%, and the probability of dark eyes given light hairs is about 4%, which is clearly larger. If you compute the chi-squared statistic, it's actually really, really big. It's 314, which means that our p-value is almost 0 and very tiny. So we would clearly reject our null hypothesis. So how do we phrase the result of that analysis? So one possibility to write the summary sentence would be there is sufficient evidence to conclude that dark-haired men have a greater tendency to be dark-eyed than light-haired men. Probability p-value is equal to 0. We looked at 6,800 people with a chi-square test. Also, a valid summary sentence would be, there is sufficient evidence to conclude that dark-eyed men have a greater tendency to be dark-haired than light-eyed men. What we cannot say is that there is sufficient evidence to conclude that dark hair, or we can say that, but it's a bit confusing. There's sufficient evidence to conclude that dark hair is associated with dark eyes. With this overview of the chi-square test, I thank you for attending this lecture and see you next week again for more on analyzing dichotomous data. Thanks a lot.